All right, hello and welcome. In this example, we are going to flip our circuit over and we're going to look at an LR circuit instead of an RL circuit. So to do that, we can reach in here and delete out each of our wires and we can reconnect them in a different orientation. So we can control R once we click on this inductor to get it upright again, and we can control R our resistor, rotate them sideways. You can also right click and rotate them this way as well. Here's the hotkeys for all those if you want to learn your hotkeys. This inductor can go down here and we'll connect it in series again. So we'll say that the voltage goes into the inductor goes into the resistor meets up with ground. Right, and that leads us back to that negative terminal. We want to measure using an oscilloscope this time, because last time we used the voltage meters, and so those gave us VRMS. So let's right click on this and we'll replace this source with a peak volt source to make it a little easier on us. So replace component, and we'll go into voltage sources and we'll grab out our AC voltage. We'll send that out. So that gives us peak volts instead of a power source like we were just using, that RMS voltage. Okay, so now we want to increase this frequency up to, like, say 10,000. See what happens at 10K. Okay, that. And from here we can use an oscilloscope to measure both the voltage drops, VR and VL, and those are going to be across each of those independent resistor and inductors. Use the total resistance value there that we get from our voltage measurement as well as our resistor value to get our total current, and then we'll use that to find XL, and then we'll use that current as well to find our total reactance in the circuit. So that's going to be our ZT, and we'll also go after our phase angle for this circuit. Our oscilloscopes can be found on the sidebar here, the fourth one down, or we can go into the Simulate tab, Instruments, and grab out an oscilloscope there. We do want to measure both of these too, so we can grab the first inductive voltage here from the positive terminal to the front of the inductor, the negative terminal on the back side of the inductor, and you can plug that in anywhere after that inductor, but before the resistor. The resistor one needs to be on channel B here, so the positive can go to the back side of, or the front side of this resistor, right here, and the negative terminal can go to the back side of the resistor. If you get those backwards, they'll read them backwards. We want to make this inductor a different color. I usually like making the inductors a different color on the oscilloscope so I can see them easier. So right click, segment color, and click on a new color in there. That way we have a blue one and a red one that we can visualize on that oscilloscope. Okay, so we want to measure the voltage drop across the resistor. That way we can get to our total current. And so we'll double click on this oscilloscope here and hit play, and we'll see what we're at. Really small, right? Really small voltage. So let's zoom in horizontal first. We'll dive in there until we see a waveform. And then we'll scale this channel A down until we see a nice stretch of our waveform. That's too much, right? It's off the chart. So one down from there, and we'll do the same. We'll try and match these two. So we'll go down until we get to the 500 millivolt. There we go. So now they're matching. We can scale this down a little bit more if we want to see it, and we can pause it right there. That way we can measure it. And so we'll move this back just a little bit so we can see our waveforms. We have our 2 meters here, and we see that one's following the blue one. That's our inductor. So we'll trace that one all the way through. And we can also trace the red one also. We can right click, select trace, and go to channel B, since that's going to be our resistor. We've changed them. And now it's following that red axis. Right, and so we want to measure the peak volts for our resistor, so we can right click and go to next max now that we're on that channel. And we'll do the same thing for this one, just so we can double check that signal there. So T1 and T2 on channel B should both be measuring the maximum peak voltage. And so for T1 and T2, channel B, we see that that's 509 for both, 509 millivolts. Right? Very little difference between the two. They got FV between the two, right? So we can use that and write that down in here as one of our voltages that we want to keep track of. So we'll say that this VR is actually equal to 509 millivolts. Right? And we can do the same thing for our inductor. We can measure our inductor the same way, but first let's get our current out of this. Let's figure out what our current is going to do. We'll say that we have our total current, and that's Ohm's law again, so we can grab out our Ohm's law triangle and say voltage on top, current, and resistance. And so if we're looking for current, we'll say voltage over resistance. So V over R, and specifically the voltage across the resistor and the voltage in the resistor itself. And so we'll do that. We'll say that we have the voltage across that resistor is 0.509, right? That's in millivolts, so I moved it down to just volts. And I'll divide that by that resistor value, which is still 6,000. So I'm going to place that in there, 6000. And that gives us a times 10 to the -5 value. So we're going to move that -5 back 1. So from this decimal point back 1. So it's going to be an 84.83 micro. And that's our current. So we expected it to be pretty small. We'll say 84.83 microamps is our new current value. It's a series circuit, so that's the current through both of those two, the resistor and the inductor. So we can use that to figure out the inductive reactance. We just have to find our VL first. So let's locate our VL on our oscilloscope here. We can right click, select trace, and go back to channel A. That's our inductor, the blue wire. And we can see that line tracing it now. And so when we right click on this and go to next max, move this one back and right click and go to next max. And we see that those are at the very top peak of both of those. That's what we want. And we know that we're reading channel A because that's where our inductor is. This blue wire here is our channel A. And so on both of these two, channel A says 855.8. So we'll round that up, 856, 856 for both. So we'll put that in. We'll say that we have 856, 856 volts, millivolts. Right? And together those should equal our total voltage for our peak volts. And we know what that is because it's given on our meter or on our original source voltage. It's only 1 volt peak. So when we add those together, we should get close to. After that, we can do our inductive reactance here. That inductive reactance is going to be Ohm's law again. We're going to go for our resistor this time though, right? Because that's going to be our XL value. And so we'll say voltage over current. So voltage over current gives us XL. So we'll solve for that. We know what our current is. We just found that up here. Current equaled voltage over the resistor. That gave us the series current. Series current can be used through both components. So we'll send this out. We'll say that we now know that the voltage drop across channel A at the peaks is 8. We'll put that in voltage form. So 0.856 divided by our current, which is really small. We'll go 84.83. We'll times 10 to the -6. To the -6. And that gives us 10,090. So we can plug that in as our XL. Our XL now equals 10K. Right? 10 kilo ohms. So to calculate ZT, we actually know what that is already. We know if we're looking for the resistance, ZT is also a part of this resistance category that we can have. We can also have one more in there, right? We can have XC, which will be later. That's our capacitors. So ZT is equal to our voltage over our current still, but this time it's got to be our source voltage and our total current. Right? We know we already had the total current, so we just got to grab our source voltage, 1 volt, and we'll plug that in for our equation here for our Ohm's law. So we'll say 1 volt peak divided by our total current, which we know is the same number up here. So we can grab that, copy it, and paste it down there. Control C and Control V there. And that gives us our total reactance for the circuit, ZT. Right? So Z is equal to 11,711.79 kilo ohms. Right? Rounded that up, made it up into our kilo ohm value, moved it by 3. Okay, so our phase angle is actually using 2 other equations. Our phase angle is the phase that the inductor has on it, and we actually see it out here. We see that they don't line up, right? The resistor and the inductor don't have exactly the same locations in terms of time, time being this x-axis. We see that the inductor rises before the resistor and falls before the resistor. And so that's given in this difference between these 2 high peaks here. That's going to be our phase angle. And so we can use our tangent equation to determine what that is. We can say that we have a theta equal to the tan, the -1 of our XL over our R. Right? And we're talking about the theta, which means it's the phase angle of the inductor. And so we're going to use that. So theta would be equal to, and we'll plug that in because we know both of those values, right? We know that we can do a function here and get our inverse tangent. That's different than tangent to the -1. So make sure if you're using a different calculator, you get your inverse tangent out and not your tangent to -1. That'll be a different calculation. It won't be a calculation. And then we want to put our XL. We found our XL. It was 10K. Right? And we want to put our resistor. We know our resistor. It was 6,000. We can exit our oscilloscope now and see that right here, 6,000 here. So we're going to plug those in. We're going to say we have 10,000 divided by 6,000. And that gives us 59. Right, so we'll write that down. That's actually a degree. So if you are, that is actually a degree. So if you are in radians, it's not going to work out. So make sure your calculator is in degrees when you calculate anything to do with time, the tangent, the sine, cosine, anything like that. So here we can say that we have 59 degrees, right? Rounded off. And so our total z equation is actually going to be 11.79 at the angle of 59 degrees kiloohms. Right, that's our total z value, zt. Okay, let us know if you have any other questions.